Hello, everyone. My name is Jesper, and I'm really pleased that I have the opportunity to present my work here today. So it focuses on exploring the use of anti-quorum sensing phages for improved therapy against Pseudomonas aeruginosa. So it all centers on this antimicrobial resistance crisis, where we're faced with rapid emergence of resistance faster than we can develop new treatment options. And in 2019, a report estimated that 1.2 million people worldwide died due to these antimicrobial resistant bacteria. And if this issue is left unchecked, 10 million people are estimated to die yearly due to these infections. And this is kind of a terrifying scenario where a bacterial isolate is resistant to all the common shelf antibiotics that we apply to treat these infections. And in this particular case, it's Pseudomonas aeruginosa, which we are focusing on developing new treatment options against. So Pseudomonas aeruginosa employs quorum sensing to control its virulence gene expression. So quorum sensing is the process of producing, releasing, and sensing quorum sensing molecules. So when the cells are at a low cell density, the molecules are also at a low concentration, and the quorum sensing regulation is switched off, and so the virulence genes are also not triggered yet. As the cells grow and reach a high cell density, the molecules increase in concentration, activating quorum sensing regulation and turning on these virulence genes that cause disease. And as a result, one alternative option is to inhibit quorum sensing using either quorum quenching enzymes or chemical inhibitors that mute the cells, confuse them, triggering them to not activating quorum sensing regulation and virulence genes. So this effectively disarms the pathogen, but without killing them. Another alternative, which is a favorite in this audience, is of course phage therapy, where we use phages to infect cells that specifically target bacteria and replicate and kind of replicates the drug, which is a super cool feature of these phages. So what we are investigating here is combining these two treatment options in a kind of dual therapy that might work synergistically. So quorum sensing regulates phage defenses and virulence, and if we equip phages with enzymes that can cleave off these molecules, we can infect the cells, have a local production at the site of infection of phages and these quorum quenching enzymes that will mute the cells, lowering the defenses of the cells, improving the efficacy of phage therapy, but also disarming any remaining or emerging phage-resistant cells. So Pseudomonas aeruginosa speaks several chemical languages. It produces the C12 homoserine lactone, which binds to less R, which then triggers a specific set of virulence genes, but also activates the other chemical languages. It activates the REL system that regulates a specific set of virulence genes, but the less R system also activates the PQS operon, producing ultimately PQS, another quorum sensing signal that binds PQSR and activates a third set of virulence genes. So to effectively mute quorum sensing in Pseudomonas aeruginosa, we equipped phages with enzymes that cleave both these homoserine lactone molecules, but also these quinolone molecules. And so we then sought to test if we can effectively reduce the accumulation of these quorum sensing molecules by infecting early exponentially growing cells, taking the supernatant and then giving them to an E. coli bioreporter that produces light when they sense these molecules. And so 6 hours after infection, we treated them with different phages. So the gray one here is an unarmed phage, and the yellow one here is an anti-homoserine lactone phage, and the blue is an anti-PQS quorum sensing signal phage, and the green is a combination of the two anti-quorum sensing phages. And we saw a significant reduction in this E. coli light production of around 30%. We also measured REL system, but that system we didn't detect many molecules on that, so I'll not focus on the REL system. 2 hours after infection, we saw a significant decrease of the PQS quorum sensing signals to a level that's below detection of limits. So this is kind of the baseline of E. coli just growing in LP. So it really demonstrates that they effectively lower the accumulation of these quorum-sensing molecules during infection. A PhD student in the lab has set up this wax moth larvae assay. So she's treating them with a burn wound and then infecting them with bacteria and then trying to rescue them with phages. So this was, of course, the next step for us because quorum sensing regulates virulence. So we wanted to test if we can actually apply that therapeutically. So treating them with a burn wound doesn't harm the larvae that much. And if you apply the phage lysate, they tolerate that pretty well as well. If you infect them with Pseudomonas aeruginosa PA14, it rapidly kills the larvae. And perhaps surprisingly, if we use the unarmed phage, they die even more than if we don't do anything. So in this case, phage therapy is not very well equipped to treat these because it triggers a specific virulent stress response in bacteria, specifically activating this PQS pathway that subsequently activates the pyocyanin virulence factor. But if we arm the phages with anti-quorum sensing enzymes, we effectively improve the therapy of the phages, demonstrating that indeed, if we equip these phages with anti-quorum sensing enzymes, we can improve the phage therapy treatment. So our phages infect phage-susceptible cells, release these enzymes in the environment, so they should be able to mute any phage-resistant cells. So we try to test this by enriching cultures with 10% resistant cells, and then doing the same as before, infecting them, and then measuring the signal from our E. coli reporters. And so 6 hours after infection, we saw a slight reduction in the C12 homoserine lactones, although it was not significant. However, the PQS system was sufficiently inhibited by our phages to a level, again, below kind of detection limit. So this demonstrates that indeed the phages can mute these co-cultures with phage-resistant cells. Another really interesting interaction in Pseudomonas is that phage infection can inhibit swarming of Pseudomonas. So this is a swarming plate where bacteria or Pseudomonas are inoculated in the middle, and then they form these beautiful patterns that we call swarming motility. If you infect a culture like that, it completely abolishes swarming. And what I think is really interesting is if we combine these two, so we have the healthy swarm in the middle, and then all these satellite colonies are phage-infected colonies. And now what you observe is that the healthy swarm avoids these infected areas. And that is super cool. So when you infect the Pseudomonas aeruginosa, it triggers this stress response, PQS stress response, that promotes virulence, but also apparently PQS serves as a warning signal, hindering the healthy swarms from colliding with the infected areas. And so in liquid culture, our anti-PQS phages could reduce PQS sufficiently. So we, of course, wanted to test if we can inhibit this physical phage defense mechanism. And although my plate is not as beautiful, you can see here that when I infect with a regular phage, the swarming Pseudomonas avoids these phage-infected areas. But if we use our different anti-quorum sensing phages, the healthy swarm collides with these phage-infected areas, and thus it can promote the spread of this phage infection. So to sum up, quorum sensing regulates both virulence and phage defenses. Also, phage infection can promote virulence and also can promote phage or activate these phage defense mechanisms. But if we can combine phages with quorum sensing inhibition, we can perhaps efficiently infect these bacteria without them launching their counter defenses and virulence programs. So hopefully this can kind of pave the way that if we can manipulate phages to trigger with the bacterial response to kind of lower the virulence and lower the activation of phage defense systems. And I would like to thank especially Kira and my supervisor, Nina. Thanks for your attention.